So we can move ahead now to understand something called as Kirchhoff's laws. So we have seen EMF, we have seen what is the let's say cells in series, cells in parallel, the combination of that. We have also seen the resistance in parallel, resistance in series. We have also gone ahead and found out what is the current that is there in a parallel combination. And from all of this, we have to finally come to the Kirchhoff's laws. So Kirchhoff's law is that part of the laws that are there in an electrical circuit which we will use to understand what this electrical circuit is trying to tell us. For instance, if you look at this, I have an electrical circuit here, and at the same time I have a common picture that we see in the country. So a lot of electrical wires that are coming out here, and it says I can explain Kirchhoff's laws. So if you can see that we have a circuit here where the current is flowing in two different directions, one from E2 and one from E1, and you have got three resistances here. Now we might have to calculate what is the resistance or what is the EMF that is there or what is the current that is being produced and all of these. So these are some things which can be used to explain or understand using the basis of Kirchhoff's laws. So looking at the history, this is an image of Robert Gustav Kirchhoff. He is a German physicist, so either the name pronunciation is Kirchhoff or Kirchhoff. Now he worked with Robert Bunsen, the person who actually went ahead and invented the Bunsen burner, and together they invented spectroscope, founded the science of spectroscopy, discovered elements such as cesium, rubidium, invented astronomical spectroscopy, and his research on electricity was in the year 1845. Now, what did he try to look at? Complex circuits. Now, when we tell complex circuits, I will show you a little later what I mean. It can even be the image in the first slide that we saw, where we had lots of electrical wires that are going to a particular junction. Now, the laws that are given by Kirchhoff provide a means of obtaining enough independent equations to solve for the following electrical circuits that are there. Or they also help us in understanding two equalities that deal with current and potential difference. So when you put them together in the form of an electrical circuit, what we can do. So let us go ahead and look at the first one, which is called as the Kirchhoff's current law, Kirchhoff's first law, or junction law. Now, as the name suggests, please keep in mind, the most commonly used or scientifically used names are Kirchhoff's law and Kirchhoff's current law. Generally, it is written as KCL, but it is also nicknamed as junction law. The reason we will see. Now, when you look at this diagram, what is it that you can see? So here is a picture of a regular intersection on the road where you can see there are vehicles which have stopped on four sides. So this is a plus junction that is there. And if we see at every instant, you can see that this road is generally divided into two pieces, right? So we can have one traffic moving in one direction, the other traffic moving in the other direction. So it can be the same for these four roads that are joining at this huge junction. This is a common everyday scene that can be seen when you are traveling at any large junction. Now, what does this have to do with the Kirchhoff's law? If you see, the name that is given is junction law. And this analogy or this explanation that is there, that we are taking of a traffic where we have vehicles that are moving, is similar to looking at an electrical wire in which these vehicles are nothing but electrons. So some electrons are still, some electrons are moving. So there can be resistance that is there. In case this was a jam-packed road, then for these vehicles to move forward, they would have to move through some amount of resistance. So for instance, if you see, if you want to take out this electron, which is this car here, it has to undergo some resistance to come out and then flow. It has to overcome that. So a junction law basically talks about that. And if you look at a junction law, it is very simple. The number of cars which are entering, number of vehicles that are entering this junction will be the same as the number of vehicles that are leaving. It can be from any side. That means we have one point that we call as the node. Yes. So if you look at this, I have current I1 and I2 which are entering the junction, and I4 and I3 which are leaving. So if you look at Kirchhoff's current law, the first law, it states that at any node of a circuit, the current's algebraic sum is 0, or at any node of a circuit, the sum of the currents into the node is equal to the sum of currents out of the node. So I can go ahead and tell from this statement sigma I is equal to 0. That means if we had seen in the slide, we have seen that there are currents I1 and I2 entering and I4 and I3 which are leaving. So it is saying that I1 plus I2, the currents entering the junction, is equal to I3 plus I4 which is leaving. So current entering is equal to current leaving, or I1 plus I2 minus I3 minus I4 is equal to 0, and this I can write it as sigma In, where n varies from 1 to whatever value that is given. Let's say in this case we can take infinity, is equal to 0. Now what I am doing here, there is negative sign, so how are you going to sum it up? So one small correction that we can do is I1 plus I2 plus minus I3. So I'm putting that in the bracket, plus minus I4 is equal to 0. So that means this positive sign is always used for entering, whatever current enters a junction or a node, and the negative sign is always used for the current that is leaving a node or a junction. So that is why this is called as a junction law, or it can also be called as a node law. But most commonly it is called as the KCL, that is the Kirchhoff's current law. So here you can see I have made justice for the summation by putting a positive sign. Only thing is I have made sure that the negative signs of the current are within bracket. So I have shown which is entering, which is leaving. So let us look at this circuit that is there. So in this circuit, I have already mentioned the dot is the node, I is the current. So if we can see what is happening here, in the first circuit, I can see that very well it is noticed that current I1 is entering, so I'll put this as positive. I2 is leaving, I'll take it as negative. I3 is again leaving, negative. I4 is entering, positive. I5 is entering, positive. So what I can do is, for the first one, I can simply write I1 minus I2 minus I3 plus I4 plus I5 is equal to 0, or I1 plus I4 plus I5 is equal to I2 plus I3. Both are correct. If I look at the second diagram that I have, all the three currents are entering. So there is plus for I1, plus for I2, and plus for I3. So there is nothing leaving. So in this case, what will you do? We will simply write I1 plus I2 plus I3 is equal to 0. See, this is an ideal case where the current is entering. But if you look at an electrical circuit, if a current enters, then it has to leave. So when we are designing an electrical circuit, it is designed in such a way that the Kirchhoff's current law as well as the second law that is there, the voltage law, both are kept in mind. The next one that is there is the Kirchhoff's voltage law. So if you can see here, it is called by many names: voltage law, Kirchhoff's second law, loop law, mesh law. So let us now try to understand what is the meaning of this voltage. Second law is something we can understand. What is the meaning of loop law? What is the meaning of mesh law? So let us have a look. We will go back to our example of road and the traffic that is there. Now if you look at this particular image that I have put here, it is a complex image of a road system that is there. So you have bridges that are there are underpasses, there are crossovers of the road, there is turning, all of these. Now in case you take, let's say, the Google map and you ask to plot a course, through this what it will do is it will try to find the shortest path in this jumble that is there. So also in an electrical circuit, we need to see what happens when a loop is formed. How much resistance should be there in the loop for how much current to reach. So for instance, if we see, when we use a regular bulb, there is hardly any fuse in the system. So that means our circuit will simply be this. It's going to be a positive, negative, maybe a switch, and that's it. So once the switch connects, then the bulb glows. So there is no resistance here. There is only flow of current and it comes out. But if you look at certain other circuits, then let's say where you're using an electrical appliance, you will have a fuse that is there also. Now the idea here is, in this entire, let's say jumble of wires that are there, if our electrical appliance, let's say a heater has to work, a certain amount of power has to be given to it. That means a certain amount of electrical energy it should receive. And that would be possible only when there is flow of current. So how is this flow of current? So if you see here, it says, starting at any node n in an electrical circuit, we form a loop by traversing through elements and returning to the starting node n and never encountering any other node more than once. So that means one junction has to be reached. It has to pass through a junction only once. If you are passing through it multiple times, then we will not be able to use this, let's say, law that is there. That's one thing. Secondly, there's a lot of energy that is wasted. So if, for instance, as you are traveling, if you are lost and you pass the same junction 3-4 times, you're only wasting your petrol and going around. Better than that is to ask someone and then find the way. Now in this case, electrons cannot ask. So what we can do, since we are designing the electrical circuit, we can design it keeping in mind the current law as well as the voltage law that is there. So Kirchhoff's voltage law. Now this is a simple circuit where I have got a battery that is there, or a cell. I have the current that is flowing. I have resistance R1, resistance R2, current is flowing and completing its path in the circuit. So it's coming back here. And if you see, I have marked the loop also. This is the direction in which current is going to flow. So first, before we try and analyze this circuit, let us go ahead and see what the law states. Then we will come back to this. So the law states the sum of voltage drop around any loop equals the sum of voltage rises, or the algebraic sum of all voltage drops around any loop equals 0. So that means we have to keep in mind the voltage drop that is there. The algebraic sum of all the voltage drops should be equal to 0. So if we come back to this circuit, where is the voltage drop and what is the meaning that it should be equal to 0? So in this circuit, let us have a look. So there was some phrase called as voltage drop, voltage rise. We'll look at that. But before that, let us have a look. We have this Vs which is already there. That is the potential difference for the entire circuit. That can be summed up here. If I can, let's say, redraw this, this is how it would look. I would have a positive, I would have a negative. This would be my R1. I would have R2 here. And this would complete my circuit that is there. Okay. So these are my resistances. This is going to be R1, this is going to be R2. This is the current which is going and coming out. Now this is written as Vs. Generally what happens, we also write this as E. Instead of Vs, we write it as E. So since I already have a circuit with Vs, I'm just replacing it by E because I've shown you an equivalent circuit here. Now let us go ahead and see what is the voltage drop that is there. In the first case, voltage drop will be IR1. And since this is the direction of flow of current, it is in the same direction. I will take IR1. Now what is happening here? It is passing through R2. So plus IR2. Now we have to be careful as to what it is. If you see, first case, it says that the first law, voltage drop should be equal to sum of voltage rises, or algebraic sum of all voltage drops around the loop should be equal to 0. Meaning, here what will be my voltage drop? So my voltage drop here is going to be negative. So minus E is equal to 0. Either the expression can be written like this, or I can write it as IR1 plus IR2 is equal to E. Now this is why it is called as a loop law. You can see that there is only one loop. What about the cases where we have got multiple resistances? For instance, if you look at the series parallel combination. So let us look at it like this. Let's say I have got an EMF here, got a resistance. Then let's say we'll put another battery here. I will draw another resistance. We'll take another battery here, positive, negative, put another resistance, and let's take another battery. So I've got positive, negative. Now if you see, I can even connect it like this. So what happens? This forms a mesh. That is why this is also called as a mesh law. Loop law, because if I take a simple circuit where in the previous case, if you see, there's only one source and two resistors, this is a simple, it's a loop circuit that is it. As the name suggests that it is given as loop here. But if you take the circuit that I've just drawn, well, it doesn't look very pretty. It looks a little scary, to be honest. You have 4 cells, you've got 4 resistors. How are you going to solve this? Simple. So first let us look at what all is. The first and foremost important thing to remember is the current should flow in one particular direction. So let's say if I'm taking the current flow from here. So before that, let's name this. This is going to be E1, E2, E3, E4. Similarly, I'll put this as R1, R2, R3 and R4. Now, we will need to keep in mind either the clockwise or anti-clockwise motion of current. Now, the clockwise, anti-clockwise is not going to do much. But if we have one particular direction, since we have got 4 different circuits here, in case we had parallel circuits, that would be slightly different. But since this entire thing is connected in one series that is there, we can keep the current to move in this particular direction. So what we will do is first we will name this. So this is going to be A, B, C, D. So what do I have here? I have got A, B, C, D, which is a rectangle. The moment you put A here, this becomes a loop. So I have completed my loop A, B, C, D, A. So this is the loop that is there. Now, important things that we have to understand. If we are going to have voltage rise, that is written as positive. If there is voltage drop, that is going to be written as negative. Now these are two important things to keep in mind. If there is going to be voltage rise, it is positive. Voltage drop, it is negative. So let us first draw the current in the circuit. Now this is going to be I4. Since I have already chosen which direction it should be, I will just make sure that I have my currents that are flowing. So this is I1, this would be I2, this is I3. Now the thing is, if you look at the direction of the cell, the positive negatives, they are different. This is positive, negative. So current is moving out, correct. If you see, this is positive, this is negative. Current should move out in this direction, no? But then we have already chosen that this is how the current should move. So that should give us an idea of where there is a voltage rise and where there is a voltage drop. If you see, in this case, this is negative, right? So this is going to be positive, this is negative. So that means, actually speaking, our current should have been upwards towards B. Here if you see, towards the negative the current is entering in. This is correct. So I'm going to have my voltage rise in E3 and in E4. Voltage is going to rise. So let me explain this again. I will just use this one diagram and I will explain. the circuit is sometimes little confusing. So first we will do it step by step. So if I take AB in my entire mesh or the loop that is there, I've taken AB. Now what is happening? The current that is there is entering the positive side. So I have E1 here. This is E2. Current is entering the positive side according to my diagram. Well, I'll keep it in red itself. So this is I1 and it is going out, which is not the direction that is there. So hence I can tell that there is going to be voltage drop. That is how it is able to go. Now, as we are moving along the given loop that is there, let us come down. What do I have? I have got E2. That is along arm B, C. I have got E2. So E2 again positive, negative that is there. And if you see, current I2 is again coming towards the positive side and then exiting. Okay, so here again what happens? There is going to be a voltage drop that is there. So A, B and BC we have seen that there is a voltage drop. Now let us look at the third arm, that is CD. So if I take arm CD, I have got the cell that is there. So this is positive, this is negative, and this is E3. But if you look at the direction of current, it is in the proper direction. So the current would start from the positive side, come at the negative side. So this suggests that there is going to be a voltage rise. Similarly, let us look at the last loop. So the last one is what? DA. So in DA what happens? Again, I have got positive, negative. Now, no matter how I have drawn it here in the circuit, my idea is to understand what happens to the voltage, whether it rises or it falls. So here, if I see, the current is reaching the negative end. So this is how the direction of flow of current is in E4. So what happens? There is going to be a voltage rise. So in this mesh that is there, or in this loop ABCDA, that is when it becomes a loop, when it is connected back here. A, B, C, D means it comes only till here. It is not connected back to A. We have two voltage drop and two voltage rise. Now where is the voltage drop that is there? Voltage drop is in E1 and E2. So two voltage drop. That means I'll have minus E1 minus E2. Two voltage rise. So minus plus E3 and plus E4. So now, can we go ahead and write the final expression that is there for this particular mesh? So for the final expression, what we can do is, again, you have to keep in mind. Now, what is happening here? There is going to be a potential drop. Correct, right? E1, that's what we have seen. E1 and E2, there is drop. E3 and E4, there is rise. So what we can do is, when we are writing the current itself, current into resistance, the voltage itself, we'll write it in that particular sign convention. So this is going to be minus I1 R1 minus E1 minus I2 R2 minus E2. Now this is in the positive. So plus I3 R3 plus E3 plus I4 R4 plus E4 is equal to 0. Now for us to break it down, I have taken loop AB plus BC plus CD plus DA for our mesh. So at each instance, whatever is the, depending on the potential drop or the potential rise that is there, I have assigned the signs. So I can group it. So here is my potential drop. This is my second potential drop. This is a potential gain as well. Here, this is a potential gain. So according to the Kirchhoff's law that is there, the sum of voltage drops around any loop equals sum of voltage rises. So for this particular diagram, I can even write it like this. Let's say I1 R1 plus E1 plus I2 R2 plus E2 will be equal to I3 R3 plus E3 plus I4 R4 plus E4. So according to the first statement that I have, or algebraic sum of all voltage drops around any loop equals 0. So here the second one doesn't talk about voltage gain, but nonetheless it is equal to 0. So you take the algebraic sum of IR and V that is there for this entire circuit. So this is when I'm looking at only one loop. This is what I have to do. What if I have multiple loops? For instance, if we have got something like this, well, I'm not going to solve it right now. I'm just giving an example. Let's say this is one resistance, that is 3 resistances. Let's say I've got another cell here, something like this. This makes things a lot complicated. How are you going to solve this? So what we are going to do is we will simply label this like this: A, B, C, D, E, F, G, H. And you can see that current was going to pass through the given nodes. So here, for this kind of a circuit, we have to find out the nodes. So the nodes are going to be B, C, F and G. What are the loops or the meshes? Now this is a mesh circuit where you can see multiple combination of resistance and cells that are there. So the loop or the mesh here that we have to solve would be A, B, G, H, A. That is, this is the first one. The second one that is there, I can have, let's say, B, C, F, G, B. And the third one, that is C, D, E, F, C. Now this as a whole combination, I will get this loop: A, B, C, D, E, F, G, H, A. If I solve these three separately, then I'll be able to get the entire mesh that is there, or one huge loop I can try and figure out using Kirchhoff's voltage law. So this is a complex loop that is there. So what we are trying to do, we are applying KVL, that is Kirchhoff's voltage law, to each of the loops. Now keep in mind, at the nodes I am applying Kirchhoff's current law. So both the first and the second law are applied, because we might have to find the current in certain cases. As I told, we might have to find resistance, we might have to find the EMF. So depending on what values we get for KCL and KVL, we can do it. Now in this case, KCL I couldn't apply because, or rather I can even look at it. If I want to look at KCL here, we can just go ahead and solve it. So let us see what we can get for KCL. I will leave this expression as it is. This I'm going to erase. So how are we going to find KCL? Now this is a very interesting question, because KCL, if I have to apply Kirchhoff's current law, the first law, it has to be applied at every node or at every junction. So here if you see, I have got junction A, junction B, junction C and junction D. If you look at junction A, I4 is entering, I1 is leaving. So I can write it as I4 minus I1 is equal to 0. Similarly at junction B, I1 is entering, I2 is leaving. So I1 minus I2 is equal to 0. At junction C, I2 is entering, I3 is leaving. I2 minus I3 is equal to 0. And at junction D, I3 is entering, I4 is leaving. I3 minus I4 is equal to 0. Now if we try and analyze this, we can see that from this we can go ahead and we can see that, let's say I'll just write it in blue color. I4 is equal to I1 from the first expression, and I1 is equal to I2. I2 is equal to I3 and I3 is equal to I4. I've just made sure that I have interchanged it. Now it doesn't mean that in an actual circuit it is going to be correct. This is an ideal circuit, an example that I have taken. So using these expressions, I can find out the value of current, and then we can use simultaneous equations to solve. So a couple of things that we have to keep in mind when we are trying to solve a given circuit that is there. We apply both KCL and KVL to the given circuit, that is both the current law and the voltage law, that is. Second thing, KVL, that is the voltage law, the loop law, should be applied to all loops. Now these loops have to be independent, that is important. So it has to be applied to all independent loops. The third thing that is there, the number of equations that we get. Now these equations are simultaneous equations. These again depend on the number of independent loops that are there. The fourth and the most important thing, KCL and KVL, that is the Kirchhoff's current law and voltage law, are both applicable to AC and DC circuits. So it is not only for one given circuit, it is applicable to both AC as well as DC circuits that are there. So as a conclusion to Kirchhoff's law, let us look at these two circuits that are there. So one describes Kirchhoff's current law, whereas the other describes Kirchhoff's voltage law that is there. Now, in the current law, if we see, according to our definition, we have made sure that all the incoming currents are given in black color, all the outgoing currents are in red color. And so we have written I1 plus I2 plus I3 is equal to I4 plus I5 by I6. That means all the incoming currents, the sum of incoming currents is equal to the sum of outgoing currents. And similarly, if you look at the Kirchhoff's voltage law diagram that is there, we have up to 7 cells that are there in this circuit. And as you can see, we have the voltage source Vs. So depending on the voltage source, we have taken the current. So here we can see that if I have taken this as the loop that is there, in this case, V1 plus V2 plus V3 plus V4 plus V5 plus V6 plus V7 minus Vs is equal to 0, or it has to be equal to Vs. Those are the things that we have to see. Now, where is this Kirchhoff's, let's say, current law and voltage law, apart from circuits, where else is it useful? So the first application that is there is something called as the Wheatstone bridge. Now this is a bridge that you can see. I mean, since it is called as a bridge, we can take it literally that it is a bridge. We have got 4 resistances, P, Q, R and S. And this central part is the galvanometer that is there. So we have a cell that is there. Now the idea is, when let's say if we take hanging bridges that are there, you can see that they generally have one pivotal point about which they are hanging. And if let's say all 4 are in equilibrium, that means all 4 have the same base level, or let's say they are at the same energy level that is there, they are all in equilibrium. Otherwise what is going to happen is there is going to be a swaying motion that is there. And this swaying motion is something which needs to be kept in check. So here when we see, we have passage of current through 4 resistors that are connected in the form of, let's say, a square, a rectangle, a diamond, anything you can take, as long as you understand what it is. So it can take any regular geometric figure that is there, but the idea here is the current that should be there passing through this bridge, that is BD, should be equal to 0. That is when this is going to be balanced. So if you look at a little bit of a history, this was designed in 1843 by Wheatstone. So this is more of a mathematical concept than let's say an actual bridge that is there. So this need not be a real life bridge, but this is a mathematical concept which goes ahead and explains resistances. Now, not sure if you can call this series or parallel combination, because if you see B and D is connected. Otherwise, what would happen? P and Q would be in series, R and S would be in series, so the combination would be parallel. But since you have this in between, we are not sure whether we have to call this in series or parallel. But if you see the current divides, I have I1, I2. Similarly, on the other side, I have I3 and I4. If you look at the direction of currents that are there, they are culminating at nodes B and at nodes D. So there's a culmination of current also at A and C. So another important thing here is in Wheatstone network, you can see that one of the resistances is having this arrow sign. Now this sign is generally used for a rheostat, or in, let's say, common terms, it is variable resistance. So now let us go ahead and solve and see what is the condition for this bridge to be balanced. So if we see, we have got four resistance, that is P, Q, R, S. Even though S is a variable resistance, it is still a resistance. Now the idea is that these four resistance are connected cyclically. So it is a cyclic connection that is there. Now in this cyclic connection, we have a galvanometer that is connected in between, let's say, circuit B and D. So points B and D, we have the galvanometer that is connected. We have a cell of EMF E. Now here what we can do, go ahead and apply Kirchhoff's current law and Kirchhoff's voltage law. So both KCL and KVL we are going to apply. So first let us apply KCL. So for KCL, if I take, let's say, at A, we don't need A, we need only B and D. B and D are our nodes here. So at B, I can tell that I1 is equal to I3, and at D, I2 is entering. Okay, sorry. We'll have to take the current through the galvanometer, which I've not drawn here. So that also we have to take into consideration. So what we will do is, this is going to be IG. So I'll mark that also. So I have IG. Now we can do. So at B, now that is very important because sometimes current through the galvanometer will not be mentioned. We have to come towards it, or we have to say that this is what we are looking at. So at B, if we see, I1 is entering and IG and I3 are leaving. So IG plus I3. This is according to KCL. And at point D, if we see at node D, I have I2 entering, IG entering, as well as I4 entering, that is there. So I can go ahead and tell I2 plus IG plus I4 is equal to 0. Now keep in mind we are doing this for a variable resistance S. Now we can go ahead and apply Kirchhoff's voltage law. So if I apply KVL to both loops, that we have two loops here. One, the first loop is AB DA, and the second loop is BC DB. So we have got two loops that are there. So we are applying KVL to both the loops. We will end up getting minus I1P minus IG galvanometer, which has its own resistance, plus I2R is equal to 0. Now this is for ABDA, that is there. So we'll just, okay. So for the second loop, that is BCDB. For loop BCDB, we can write I2Q plus I4S minus IGG is equal to 0. So now in both cases we can see that IGG is common. So before that, we have to do a little bit of modification. Now, the idea is, since we have used KCL, that is Kirchhoff's current law, we can do a slight replacement that is there. Now, I3 and I4, we can write it in a different format. Now, I3 will be equal to what? It was nothing but we had written it as I1 minus IG. I can write it in this particular format. And I4, I can write it as nothing but I2 plus IG. That is when I can tell that the current that is leaving the cell comes back to the cell. That is if this direction is like this and not downwards. So keeping this in mind, we can actually substitute that here and we can see what we get. So on substituting those values, we will end up getting I1P is equal to I2R, and let's say in this case it is going to be I3Q or nothing but I1Q. Since we can take the current to be the same, I will end up getting it as I1Q is equal to I2S. Now, since I've got this I've got from the condition that we are looking at the balancing condition. And the balancing condition is that the current through the galvanometer is 0. So Ig is equal to 0. Now we end up getting this to be the ratio P by Q is equal to R by S. So for a balanced Wheatstone network, the condition is that the ratio of resistances, that is P by Q, is equal to R by S. That means resistances above A and C should be equal to the ratio of resistances below A and C. Now we need not always take it like this, but then this is a standard format that is there, and this is applicable in a lot of, let's say, lab experiments that we do. It can also be used apart from the labs, let's say in household circuitries and all of these places, it can be used. But mostly in the lab session, let's say like when you look at experiments such as meter bridge or potentiometer, this comes in very, very handy, where we are able to see something called as the null point, where this entire circuit is balanced. Now let us look at some of the cases that are there for balanced Wheatstone network. Or let's say what are the important things that are there which are related to a balanced Wheatstone network. So in a balanced Wheatstone network, the first thing and the foremost thing that is there is the potential difference across the galvanometer is 0. The potential difference is always going to be 0. Now once we have achieved the balancing condition, that is the current through the galvanometer is 0, you replace the galvanometer by any resistance. The circuit will still be balanced. Now, why I say the circuit will still be balanced is, if you look at this condition, I have told that Ig should be equal to 0. That means there is no current passing through BD. That is no I through BD. So if there is no current passing through the branch BD, I remove the galvanometer and put any other resistance that I want. It is still going to not affect the circuit. So it remains unaffected once the balancing condition is obtained. So that is very important. Without obtaining the balancing condition, you cannot go ahead and do that. Now, another important thing that is there is, in case we interchange the cell and galvanometer. The circuit will remain balanced. So this is very important. The circuit will still remain balanced if we interchange it. So if we have a look, what is going to happen? This E, which was in between A and C here, you put it here, it will be in between B and D. So what is going to happen? The circuit will look the same. It's a different perspective of looking at the same circuit. So it's not that we're looking at a new circuit or a different circuit. No, it is the same circuit. But what we have done is, it's just like a Rubik's Cube. We have done a few modifications here and there. We turn the cube, the slides of the cube, and you get a different pattern. It's exactly the same thing. So what I've done is, instead of looking at it in this particular format, I have looked at it in a slightly different format. Now another important concept that is there is the effective resistance that is there. Now effective resistance we can talk only when we are looking at, what do we tell, the balancing condition, that is Ig is equal to 0. So effective resistance where? Between A and C. Where there is no connection between A and C, what happens? At A it branches out, at C it comes back. So between A and C, what is the effective resistance? It is given by this particular formula. R effective is equal to P plus Q into R plus S divided by P plus Q plus R plus S. Now this is an important formula that is there for your entrances. So in case of Wheatstone network is given and you are asked to calculate effective resistance, you can directly plug it into this particular formula and you will get it. So you will get the effective resistance that is there. So these are four important things or four important points that are there when we talk about the Wheatstone network. Now let us look at the application of, let's say we have seen the applications of Kirchhoff's current and voltage law in the Wheatstone network. Now let us look at the application of Wheatstone network in another important concept in physics called as meter bridge. Now what is a meter bridge? A meter bridge is a practical concept. So when I tell practical, it means it is a concept which practically uses Wheatstone network. Because if you see, Wheatstone network is a mathematical construct. There was no physical significance for this. So now we have come up with, back tracing it, we have come up with a physical significance, that is a practical concept of the Wheatstone network, which is our meter bridge. And this is very much helpful in determination of unknown resistances that are there. So what I have given here is just a schematic diagram of the meter bridge. So if you see, it doesn't look anything which is vaguely familiar or something which you can understand. But here you can see that there is one L shape here, there is something here, and there are knobs. So let me take you to the practical connections that are there. That is going to help us understand this. So in a lab setup, this is how we are going to connect. Here we have got EMF, that is our cell that is there. We've got a resistance box, a plug key, a galvanometer, and this is our meter bridge that is there. And this is a jockey. Now what is going to happen here is, we have got two ends, that is A and B. Not able to see, I'll use a different color. Yes, A, B. Now AB is 100 centimeter in length. 100 centimeters. So that means it's a 1 meter long scale or 1 meter long wire that is there. Now the idea here is, we have this cell which is giving us a constant current or a potential difference. So this is going to be one end of our resistance. So this I can take it as let's say R1. I've got a resistance box which will contribute to R2. Now, there will be one point along this where current is going to be 0. Ig is equal to 0. So that deflection in the galvanometer, we can see that there's no deflection. Now, this is going to be R3 and the other end is going to be R4. I mean, I have given you an outline of what it is. I will explain this in. So let us look at the working of a meter bridge. Theoretically, we have already discussed it a little bit. So we will look at the practical working of it, and then we will move into the rest of the theory that is there. So this is a fully functional meter bridge that is there, which consists of P and Q, where P is an unknown resistance, Q is the resistance box, capital G is the galvanometer. You have a jockey that is connected to the galvanometer. You have a Leclanche cell that supplies EMF to the circuit and the key to complete the circuit. Also, this length AC that is there is a wire that we use. Now, let us look at the parts separately. First, we have thick strips of copper. Now, these thick strips of copper that are there, you can see that there are two gaps in between the copper pieces that are there. And this basically aids in conduction. So the moment we connect our cell here, the current is going to pass. Now in these gaps, we will connect the resistance as I have shown earlier. So thick strips of copper is used basically to help the clean or the faster conduction of current. Because copper is a good conductor, even a very small current that is produced by a Leclanche cell, which is an electrochemical cell, will help in conduction of current. The second thing that we have here is the wooden board. So this entire setup is mounted on a wooden board so that there is no grounding and loss of current that is produced by the cell. This is most important when we are using an electrochemical cell. Because in a Leclanche cell or in a Daniell cell, we have two electrodes and we pour the electrolyte solution. So the amount of current that is produced here is very small. It is not negligible, but it is small. But if we do not place these copper strips on a wooden board, but rather place them on the table itself, then there is going to be grounding and we will not be able to perform the experiment. So for that reason, we will make sure that the wooden board is used for grounding. Next, we have two gaps, G1 and G2. Now these gaps are very important because this will connect the arms of our Wheatstone network. So this is a practical working Wheatstone network, the meter bridge that is there. So in gap G1 and G2, standard resistances will go. So in gap G1, we will have an unknown resistance which we will call as P. And at the same time, in gap G2, we are going to have a variable resistance or a standard resistance, which is our resistance box that is there. So here we can see that G1 is forming P and the resistance box, the variable resistance, a rheostat or a resistance box here is going to form the arm Q. Now there is a point B in between G1 and G2 which we connect to the galvanometer. Now the galvanometer is very important because in the Wheatstone network, the galvanometer will decide on the balancing condition. That is, current through the galvanometer arm should be equal to 0. And that is what we are arriving at here. Now one end of the galvanometer will be connected to point B, which is a contact between the two gaps, and the other end will be connected through a high resistance to a jockey. Now it is called as a jockey because it is similar to the rider on a horse. Now, what does the rider on the horse do? He controls the motion of the horse, the speed of the horse, and also the direction in which they have to go. So this jockey here does the same thing for this particular wire. So this galvanometer that is connected here, make sure that there is a contact between point B, that is in between the two resistances that we have, P the unknown and Q the known or the variable resistance, and arm AC. So we have got two arms, so two resistances, P, Q, and the other one that comes because of length, AC. Next, we have our uniform manganese wire, AC. Now, this manganese wire is uniform in both length and its thickness. We also use manganese wire because we know its resistivity, and it is easier for us to get the resistance, and this wire basically is available in the market at a less price compared to any other material. So we can use the manganese wire. Now, what is the jockey going to do? The jockey is going to ride along the manganese wire AC as shown right now. So right now I have connected everything that is required here except for the key and the source of voltage here. So we will connect that. So from end A, I will go ahead and connect a Lagrange cell, and that connected through a key is going to go and reach the other end. So here you can see that this circuit is complete. So you have the Lagrange cell through which current is going to pass through this copper wire through an unknown resistance P. Through contact B, part of the current is going to go through the galvanometer and reach a point in between A and C. We have an we have a variable resistance Q through which, since it's a resistance box, we can remove specific amounts of resistances and calculate what is the point of balancing length. So this completes our entire circuit. So now let us go ahead and see what happens. So as soon as the key is plugged in and we are moving the jockey front and back, let us have a look at the galvanometer. So in the galvanometer, we need to have zero deflection. So you can see at this point, J, there is zero deflection in the galvanometer. Now in general, what we do is we slide it from A to C or from C to A. It can be in any direction as long as the galvanometer will show zero here in its digital meter that is there. So if I go slightly back, I can show you that. So here you can see there is no deflection in the galvanometer that is shown. Now P and Q form two arms of the Wheatstone network. What are the other two arms? So the other two arms are length L1 and L2 that is there here. So how can I tell L1 and L2 are the resistances here? So if you recall, we had previously found out that resistance depends on the length. So keeping that idea in mind, we can use L1 and L2 as the other two arms of the Wheatstone network, which give us a significant amount of resistance that is there. So since we have seen this as the experiment, now let us go ahead and see what we get when we try to use this in a standard Wheatstone network. So in the Wheatstone network, we had the relation P by Q is equal to R by S. So in this case, what is R and S? P and Q we have already defined. Now R will be nothing but length AJ and S will be length JC, which means P by Q will be equal to L1 by L2. Now we can quantify this in a slightly different way. So if I tell L1 is equal to L, then L2 will be nothing but 100 minus L in terms of centimeter, or I can write it as 1 minus L in terms of meter, but I will retain it as 100 minus L. So P, the unknown resistance, is equal to Q times L by 100 minus L. The unit is going to be in terms of ohms. So this is how we find the value of an unknown resistance using meter bridge, which works on the principle of Wheatstone network. So the next important concept that is there here is nothing but a potentiometer that is there. So in a potentiometer, if we see, it is nothing but an extension of the meter bridge experiment that we have just seen. So let us look at the principle of a potentiometer. The principle states that the fall in potential across any portion of the wire is directly proportional to the length of the portion of the wire, provided The wire is of uniform area of cross section and has a constant current flowing through it. So if you see, the fall in potential across any portion of the wire is directly proportional to the length. So in the previous case in Wheatstone network or the meter bridge, the practical application, we went ahead and we took the ratios of the length equal to the ratios of the resistances. So which is very much valid here. So let us have a look as to what we are going to get. So for instance, if we see, we know from Ohm's law that V is equal to IR. And we have also seen that resistance is equal to resistivity into length by area. So therefore, our potential difference V will become I times rho L by A. Now, the second important thing that they have told us, we are talking about a constant current that is flowing. So, if I take my expression V is equal to I times rho L by A, if I take current as a constant, we know that the resistivity of a given wire is also a constant. And the area that is there of the wire also is a constant. Because if you are taking a wire of uniform thickness,